Hey everybody, we're going to be looking at lesson 10.5, which is finding the probability of A and B. So yesterday we looked at finding the probability of A or B. So there are some differences here. There is some vocabulary to look at. Independent events, which is two events such that the occurrence of one has no effect on the other. Dependent events, where two events such that the occurrence of one alters the probability of the other. And then there's conditional probability that says if that event B occurs given that event A has already occurred, is called the conditional probability of B given A and is denoted. So we put the probability of B and then that slash is a given. So when we're looking for the probability of A and B versus or, we're going to be multiplying. So just to show you an example of that without using a word problem, we have been given the probability of A and the probability of B. So to find the probability of A and B, we multiply 5/8 times 4/5. 5 times 4 is 20. 8 times 5 is 40, and that could also be reduced to 1/2. On the next page here, we are going to be looking at an independent example using the standardized test practice question here. So it says, for a fundraiser, a class sells 150 raffle tickets for a mall gift certificate and 200 raffle tickets for a booklet of movie passes. So you buy 5 raffle tickets for each. What's the probability that you win both? So both here is kind of the key word because, like, let's say we win, like, what's the probability of winning the mall gift certificate or the booklet of movie passes? So the probability that M and B happens, so we have to multiply the probability we win the mall gift certificate times the probability we win the booklet of movie passes. So we bought 5 tickets out of 150 for the mall and 5 out of 200 for the movie passes. And when you multiply that in your calculator, you get 1 out of 1,200. Okay, so looking down here, the probability of dependent events. So we're looking at the probability of A times the probability of B given A. The same idea here, we've been given A, B given A, and what it would be both. So the probability of A and B is 0.4 times 0.4, so that would be 0.16. Looking at this example down here, it says find the probability that a listed person has A, so we're looking at blue eyes, and then B, a male has blue eyes. So let's just look at like how many people we're looking at here just to get a few numbers. So 27 plus 12 is 39, males and females with green eyes, 44 with blue eyes, 53 with brown eyes, and 64 with hazel eyes. There's 100 males and 100 females, so there's 200 people total. So the probability that they have blue eyes is equal to, so that's for A. So how many people have blue eyes? Well, if you look, there's 44 people total with blue eyes out of 200 people total. So if you divide that in your calculator, you get 0.22, which is 22%. For part B, the probability that a male has blue eyes. So blue eyes and is a male. So the males that have blue eyes are 35 of them out of 100 males total. So that would be 35%. All right, so looking at this example here, we're going to be comparing independent and dependent events. So the problem says you randomly select 2 marbles from a bag. So there's 15 yellow, 10 red, and 12 blue marbles. What's the probability that the first marble is yellow and the second one is not yellow? So that would be the red or the blue. So something that's helpful if we look at the total marbles, that would be 15 plus 10 plus 12, so that's 37 total marbles. So the question says for part A, what's the probability of the first marble being yellow and the second one being not yellow if we replace the first marble? So what that means is we took out a marble for our first draw, I guess, and then we put it back. So we look at the probability of the marble being yellow times the probability that it's not yellow. So the probability of it being yellow would be 15 out of 37 times not yellow, so there's 10 red and 12 blue, so that's 22 out of 37. And in your calculator, that comes out to 0.241, which is 24.1%. When you're doing this in your calculator, if you're using a graphing calculator too, you can put these in parentheses when you multiply them to help with getting the right number. And then let's compare it to being dependent though. So what it says is you do not replace the first marble. So it's the same thing. What's the probability of it being yellow times the probability that it's not yellow? But so the probability that it's yellow is still 15 out of 37 times 22, but we didn't put the marble back, so that's 36. So when you divide that in your calculator, you get 0.248, which is 24.8%. Okay, so then when we look here, solving a multi-step problem, we're going to talk about making kind of the tree here. So what it says is that a study reports that 69% of adults wear a seatbelt while driving. So it says a high school student in the car wears a seatbelt 66% of the time when the adult is wearing it, but only wears it 26% of the time when the adult does not. So the question is asking us, what is the probability that a high school student in the study wears a seatbelt? So let's make a tree diagram here. So let's just start at the top. So it says 69%, so that's 0.69 of adults wear the seatbelt in the study. So what that means then, if you take 100% minus 69%, then 0.31% of adults do not wear their seatbelt. So now let's split it up because we're looking at the students here. So it says in the story that when the adult wears the seatbelt, 66% of the students do. So if we think about that for a second, when we're looking at 69% of the adults are wearing the seatbelt, 31% are not, so then there's the 66% of students that do. To figure out how many are not, we have to take 100 minus 66, so 34% then of students are not wearing their seatbelt. So this is student wears seatbelt, and student does not. And then on this side, the adults who do not wear a seatbelt. So if the adult isn't, it says then 26% of the time the student does not either. Or I'm sorry, the 26% of the time they do. So I'll just put student does over here. So then 100 minus 26 would be 74%. So the student does not. So here, to figure out the probability that a high school student wears their seatbelt in this study, we have to take the 69% of adults who do times the students that do, and then we have to add it to the 31% of the adults who don't times the students that do. So in your calculator, you'll take 0.69 times 0.66 plus 0.31 times 0.26. And when you do that, you get 0.536, which is 53.6%. All right, let's do one more like that. So it says students get a B in math studies 75% of the time when they have Mr. Sauter. So 75% of the time, Mr. Sauter. But they get a B only 55% of the time when they have Mr. Anderson. So each teacher gets a student determined by a scheduling system. So it says here 33% of the students are in Mr. Sauter's class and 67 are in Anderson's class. It says, what's the probability that a randomly selected student gets a B? So let's make our tree here. So the students are either going to be in Anderson's class or in Sauter's class. So for Anderson, he gets 67% of the students, where Mr. Sauter is getting 33%, and it tells us that. So it says Mr. Anderson's students get a B 55% of the time. So that would mean 45% of the time they're not getting a B. For Mr. Sauter, they get a B 75% of the time. So that means 25% of the time they're not getting a B. So to find the probability that they get a B, we have to take 0.67 times 0.55 plus 0.33 times 0.75. So in your calculator, 0.67 times 0.55 plus 0.33 times 0.75. And in your calculator, that'll give you 0.616, so that's 61.6% of the time. All right, and that is all of the examples I'm going to do here. If you would like to see more, you're welcome to take a look in your completed note packet on Schoology. Thanks.